Welcome to today's Explainer. We're going to dive right into how the hidden microscopic rules of chemistry actually govern everything around us. We are talking about everything from keeping our winter roads safe to drive on to powering the smartphones right in our pockets. We'll be looking at the totally fascinating mechanics that dictate how solutions behave and how scientists have figured out ways to harness these invisible properties to do real, visible work in the real world.
So what do de-icing an airplane and a TV remote have in common? I know, it sounds like a totally bizarre comparison. What could a massive jet coated in ice possibly share with the small piece of plastic sitting on your coffee table? Well, the answer lies entirely in how dissolved particles physically manipulate their environment and transfer energy. In both cases, we are leveraging the exact same fundamental rules of chemistry, specifically how particles interact when they're mixed together and how we can force those microscopic interactions to work to our advantage.
Okay, here's our roadmap for today. We'll start with an intro to colligative properties, then move on to freezing, boiling, and vapor. After that, osmosis in the real world, the electrolyte plot twist, harnessing spontaneous chemistry, and finally, the anatomy of a galvanic cell. Let's get into it.
Section 1. Intro to Colligative Properties.
Colligative properties are honestly fascinating. They are a subset of behaviors that depend entirely on the total number of particles in a solution, not what those particles actually are. Let me say that again because it's absolutely crucial. It doesn't matter what the chemical identity of the particle is. It only matters how many of them there are. Whether it's sugar, salt, whatever, if the particle count is the same, the effect is the same. This brilliantly illustrates a concept called vapor pressure lowering. Think of it like this. In pure water, solvent molecules at the surface can easily just escape into the gas phase. But in an aqueous solution, the added solute particles physically crowd that surface. They act exactly like a packed dance floor that blocks people from leaving, hindering vaporization and forcing the overall vapor pressure to drop.
Section 2. Freezing, boiling, and vapor.
Because those crowded particles lower the vapor pressure, the solution's entire temperature profile actually shifts. It now requires a much higher temperature to boil and a much lower temperature to freeze compared to a pure solvent. We exploit this freezing point depression every single winter. By tossing rock salt or calcium chloride on icy roads, that salt dissolves into the thin layer of surface water, drastically lowering its freezing point. Suddenly, the winter air just isn't cold enough to keep it frozen, the ice melts away, and our roadways stay safe.
Now, take this up to 30,000 feet. In aviation, the stakes are obviously way higher. You certainly can't use corrosive rock salt on a multi-million-dollar jet, right? Instead, they use heated, non-corrosive covalent compounds like glycols and spray them directly onto the airplane's control surfaces. This safely depresses the freezing point, stripping away the existing ice and leaving a protective shield that prevents dangerous new ice from forming during takeoff.
Section 3. Osmosis in the real world.
These same principles of concentration don't just melt ice, they also govern the flow of water through semi-permeable membranes. And this is a process that is literally keeping you alive right now, osmosis. When two solutions of different concentrations are separated by a membrane that lets water through but blocks the larger solutes, water naturally flows toward the higher concentration to balance things out. This rush of water builds up hydrostatic pressure, what we call osmotic pressure, until the transfer rates finally equal out.
But what happens if we actively push back against this natural osmotic pressure? Well, if you apply massive mechanical pressure to the highly concentrated side, say seawater for example, we can actually force the water molecules to travel backwards through the membrane, leaving all the salt behind. This is reverse osmosis. It's the exact technology used all over the world for the large-scale desalination of ocean water to produce clean drinking water.
And you know, the stakes are incredibly high in medicine when it comes to osmotic pressure. Intravenous fluids must be perfectly isotonic, meaning they have to exactly match the osmotic pressure of our blood serum. If you inject a hypotonic solution, one with too few solutes, water rapidly rushes into your red blood cells by osmosis. This causes them to expand and literally rupture in a fatal process called hemolysis. On the flip side, a hypertonic solution aggressively sucks water out of your cells, causing them to shrivel and die, which is known as crenation.
Section 4. The electrolyte plot twist.
So just when we think we've got the math of colligative properties all figured out, electrolytes come in and introduce a completely fascinating complication. Remember, it is all about the particle count. Simple non-electrolyte molecules like glucose or sucrose dissolve as single intact units. But strong electrolytes like sodium chloride, they dissolve and immediately dissociate.
A single unit of salt breaks apart into a separate sodium ion and a chloride ion, effectively multiplying its colligative impact on the solution. So 1 mole of salt actually yields 2 moles of particles.
But of course, there's a catch, and we represent this with the Van Hoff factor, or I. This value compares the predicted number of particles to the actually measured number. Notice how salt is predicted to yield exactly 2 particles, but the measured value is only 1.9. Why is that? Well, in a solution, some of those oppositely charged ions are actually still attracted to each other, briefly clumping together into what we call ion pairs. They act as a single particle just long enough to slightly reduce the overall mathematical effect from what we would perfectly predict.
Section 5. Harnessing Spontaneous Chemistry.
Now we're pivoting from the passive properties of solutions to seeing how we can harness active electron flow. When a solid copper wire is placed directly into an aqueous solution of silver nitrate, a spontaneous redox reaction kicks off. The copper oxidizes, naturally giving away its electrons and dissolving into a blue solution. At the exact same time, the silver ions are reduced. They grab those free electrons and deposit as solid gray silver. But because they are physically touching, this transfer happens right at the surface of the wire, meaning we can't capture any of that energy.
Which leads us perfectly into Section 6, Anatomy of a Galvanic Cell.
To actually capture that energy, we have to get a little clever. Enter the galvanic cell. By entirely separating the copper and the silver into isolated half cells, we change the game. Now, the only way copper can give its electrons to the silver is by traveling through a long external wire. This forces the transferring electrons to do useful electrical work for us along the way. And to keep the charge from building up and stalling the whole system, a vital salt bridge allows inert ions to flow back and forth, continuously maintaining the electrical balance.
In this electrochemical setup, each side has a very specific job. We firmly define the anode as the electrode where oxidation happens. In this case, that's our copper foil losing electrons and dissolving away. Conversely, the cathode is the electrode where reduction takes place. That's our silver foil, which is gaining electrons and actually growing thicker as solid silver plates right onto it. Now, drawing out these full diagrams every single time gets pretty tedious, right? So to communicate this easily, chemists use cell notation. It's a highly abbreviated shorthand that describes the entire galvanic cell. We always read it strictly from left to right, starting with the anode and ending with the cathode. We use a single vertical line to show when the state of matter changes, like moving from a solid wire to a liquid solution, and commas to separate different chemicals that are mixed together in the same phase.
So, how do the invisible behaviors of dissolved particles dictate the visible rules of our universe? Well, think about it. From the exact concentration of dissolved salt keeping our winter roads clear and our blood cells perfectly intact, to the highly directed, spontaneous flow of electrons through a galvanic cell powering the remote in your hand right now, these microscopic mechanics dictate our reality every single day. It really makes you wonder, what other macroscopic miracles in our daily lives, like the buffer systems and their precise capacities regulating our oceans, or the colloidal dispersions causing the Tyndall effect in our atmosphere, are just waiting to be explained by invisible, microscopic math?